Hello?
Hi.
Yeah. Yeah, so you were saying about you told, I think it cut off right at when you told me about you were looking for entry-level positions. Yeah.
Yeah. I mean, that's basically the summary, is that I'm like a new grad looking for soft ends roles. The only thing that's changed since last time is I have a bunch of interviews scheduled this week. So hopefully
hmm
be pretty prepared for those.
Got it. Yeah. And it'll be good to, like, if you have lead code premium, or if you can filter questions by those companies and look at just like get an exposure of like what kind of questions they are asking, like
Right.
most frequently, that might help.
Okay, yeah, that's a good idea.
So, cool. So, yeah, so we'll follow the similar format as last time. We can do a couple of questions depending on the speed, and then we'll reserve like last 5 to 7 minutes for feedback. Yeah.
Great, that sounds good.
Cool. So for the first question, let's do this one. So let's say you're given a list of meetings, right? And based on this list of meetings, we want to find out um, what is the minimum number of meeting rooms which are needed to host all these meetings, right? So let's say an example is like this. Here you're given a bunch of meetings, start time and end time, and then the output is 2 because like the first 2 meetings, they overlap. So we'll need at least 2 rooms to host those 2 meetings.
Okay, great. I'll just draw like a diagram here. Two,
Mm-hmm.
5, 7, 9. Okay, so, okay. Um, Couple questions about the input. Are the start and end times guaranteed to be whole numbers?
Yes, yeah.
Okay. Integer sentence. Um, are the time intervals open or closed? Meaning, like, if I have a meeting from 1 to 4 and one from 4 to 5, do those conflict or are those fine?
Yeah, good question. So they do not conflict. So you can place them in the same meeting now.
Okay. Okay. So I think that's kind of all I need to know. So we have a bunch of intervals, and we want to know, so the sort of geometric interpretation of the data is like, I'm thinking of like drawing these time intervals on the number line, like I've done here. And then once you've done so, the minimum number of rooms needed to schedule all the meetings is just the deepest stack of concurrent meetings, because um, basically, like, I mean, it's pretty intuitively clear, I think, that if you have 5 meeting rooms and there's at most 5 meetings at once, you can always, you know, you'll have enough meeting rooms. And then similarly, if you had only 4 meeting rooms, but there was 5 meetings going on at one time, they need to be stuck. I guess this is like, the assumption is that there's 1 room per meeting. Is that true?
1 room per meeting.
Yeah. Okay. I figured. But okay. So yeah, 1 room for concurrent meeting. Yeah. Okay. Great. So I think all I should have to do is sort of, well, I don't know yet how to do this, but what I want to do is to compute the sort of, yeah, like I said, the deepest stack, or like the widest overlap. Well, maybe not width is not the right word, but the most number of intervals that are concurrently intersecting. So you think about how I would do that. Hmm. So I guess naively, we could think of this as like an intersection graph where each node is an interval and each edge is the edge relation is whether two intervals intersect. So we can get an n squared times solution, but I hope to do better. So idea intersection graph O of n squared to check all pairs, and then this sort of, we want to find the largest clique. Well, actually, finding the maximum clique in a graph is a hard problem, so maybe this isn't a nice approach. Let me keep thinking. So suppose for now we sorted the input by start time, because that's probably useful. Then we can do something that's kind of left to right. And if we were to do that, let me think. I guess you could have maybe like two queues, sort of. Like you process the input in order of start time, and then you keep a data structure, probably a queue of currently open intervals, like intervals that you currently that are currently running, meetings that are currently running. And if that queue is instead sorted, if it's like a priority queue where it's sorted by end time, then I should be able to efficiently sort of, every time I see a new start event, before I process it, I can like dequeue from the queue as many times as I need to make sure the intervals that have already closed are not still in the data structure. And then like, I mean, it's not exactly a sliding window, but it's sort of vaguely like that, where I'm, actually, I could maybe do this even more simply. Oh, yeah. Yeah, of course. Okay. So that's a little overkill, but like, so let me see if this works. So idea, think of each interval as a pair. Oh, I forgot to ask this, but is every interval well formed and non-empty? Like, is end always strictly greater than start?
And yeah, end can be equal to, so if it starts at 1, yeah, it'll always end at 1 more than the start. Yeah.
Okay, perfect. That sounds good. Yeah, so thinking of each interval as a pair, so forget this idea. I mean, I don't like that one. So think of each interval as a pair of events, like a starting event, a start event, and an end event. And then if I just process a stream of events, of sorted events, so let's say events sorted by timestamp, and then you just like increment a global counter, incr on start, vector on end, and then return the overall max of the counter. So keep counter. Okay, so this idea I feel like will work and gives us linear, well, n log n time, which I'm guessing is optimal. Probably hard to prove, but I'd be surprised if you could do this in purely linear time, unless the input was already sorted or something. Is it safe to assume that the input is already sorted, or no?
Input can be in order.
Yeah, okay. So we'll sort it ourselves. And I'm pretty happy with this time complexity. It's not like I really am bothered by the log n. So yeah, I think I'll start getting into the code, because I think I have a pretty clear idea. Do you want any more explanation of the approach, or does it make sense where we're going with this?
Yeah, this looks good. Yeah.
Great, sounds good. So I'll pick a language here. Okay, so an interval start. Can the start and end times be negative integers, or are they always non-negative?
They are only positive here, 0 or positive.
That sounds good. So half open non-empty interval. And
What does half open mean? I've never heard of it.
yeah,
What is it?
it's a jargon from mathematics that means like if you have the interval from 1 to 4, that the half open interval includes 1 and excludes 4. So like 4 is kind of outside of the interval. So it's you could also
Okay.
like left inclusive would be a synonym for that.
Makes sense.
Okay, and then the function is the num meeting rooms for meetings would be a list of interval, and we want to output the number of meetings. Okay. I think I would just let's think about this. So yeah, so event start and so meetings dot and let's see here. Sorry, for meetings. I want to iterate over this. I guess this has to be copy technically. Are we running code in this interview or just writing code?
No, just writing. Yeah.
Okay, good. So I want to iterate over all the meetings, and then
Actually, we want to run it because this is a different language. So
okay, yeah, that's fine. That's fine. We can do that.
Yeah.
Okay, so I'm iterating over all the meetings, and then for each one of them, I'm going to produce a pair of events. So flat map the meeting M into the two events, which are how will I write this? Iter wants really. Oh, I could do it like this. So start. Could these use events star, but right. So start and let's start and end and not end into iter. So this is now so let's events equals this. I wanted sort events. So let's say events should be a list or a vector, and then at this point we can make sure our code is doing what we want, and we can print things. So let's plan to do that, and then come back to the answer. So for convenience, we'll say full interval continue start end. Maybe that's not necessary. We'll come back to that. So right. So let's pairs list of comprises a list of what do we have? So let's say 4, 1, 2, 5, 7, 9, and well, let's say so this to iter map start end into interval start end. Okay, so that's that, and then collect that into vec, and then so we can print that as well. Pairs, and then we want to run num meeting rooms on. This isn't pairs anymore, just meetings. Meetings. Okay, let's see if that code compiles. We have two definitions of main, so I'll delete the first one at the top of the file. It's complaining interval is not debuggable, I'm guessing. Oh, events. Yeah, sure. Okay. These can both be copied. Okay, and into iter map. Oh, I need parens here to be structured to tuple, but otherwise that should be good. Rust types. Yeah, this is okay. This is an outdated version of Rust, but that's fine. I just need to deref here. And the complaint now is returns value, and that's okay. So it's annoying that they do that, but fine. I'll just do this instead. Okay. There must be an yeah, that's true. Complaint is returns. Oh yeah, and I'm doing it in here. Okay, fine. Great. So our input here is the first thing printed. It's the 3 intervals. And then we're printing events on line 63, which is these start and end times in sort of mixed in this heterogeneous data structure list, really. But we'd like to sort it. So let's say we do events.sort unstable by key. Sure. So info event would be a good way to do this. I think, yeah, I'll write it like this. I mean, time itself do so start T and T. I think I'd actually maybe do this a little differently if I had to, but it's fine. So sort E dot time. Okay, cool. So that should probably sort it for us. Let's see. Oh, there's no method. Sorry. Call the method. There we go. Okay, so now we have this mixed list of events, but it's also sorted. So we're getting pretty close. So I'll comment out the print statements, and then all we have to do now, I think, is just say like, let mute rooms equals starting 0, and then like for E in events, match E start. We don't even need the time actually. We say rooms plus 1 and end rooms minus equals 1. And at the end, we want to know the maximum of numbers. So I'll write it like this. Events into iter. Say that. Well, let's return it. So to iter map E into all this, and then of these, I want the max wrap. Wrap or 0. Okay, which is like for numbers. Oh, yes, right like that. Okay, so and that should do what else I want. Expected one of. Let's see here. Is it the braces that I have too many of? What's the complaint here? Oh, it's commas. Yeah, that's fine. Okay, so the code ran, but we didn't print anything. So I might as well actually show what the answer is. And it should be 2, and it is 2. Yeah, so I think it might literally just be done here. I want to check the edge cases though. I haven't thought deeply about open and closed intervals. But before we get to that, do you have any questions about the code we have so far? Because a lot of it is using these like iterators and sort of Rust specific syntax. So it might not be clear yet. Yeah.
Yeah, I can make some of it. Yeah, it looks, I mean, you're using a map and then you're matching on it. And then whenever you have a start event, you're incrementing it and decrementing it. And then you're trying to find max across all of these matches, I guess. Is that the right idea?
Yeah, exactly. So like it's like this anonymous function which takes an event. The last expression is the return value of the anonymous function. So for each event, we return the current number of rooms. And then of all those, we want the maximum. Exactly.
Okay. Looks good. Yeah. So what are like the different tests you're considering? You don't necessarily have to write them.
Yeah, I guess importantly, you should do like an empty list, which I think we've handled because we have this like default value for the maximum, which handles empty lists. Nice. And there's we want to do ones where the input is sorted, isn't sorted, like a big input for performance if you're trying to kind of manually verify that it takes linear time, for example, or nlog n time. Yeah, like lots of disjoint intervals, lots of really heavily stacked intervals, and yeah. I think that would be pretty good.
Sounds good. So let's move on to a different problem.
Okay.
So for this one, let me copy the question. Hmm, Let's say on line number 1, or inside line number 3. So you're given this input on line number 7, which is you're given a grid, right? So on the grid, each point refers to a elevation, like the height at that point, right? So if you look at it, 0, 0 is at height 1, 0, 1 is at height 1, and so on. So each of the locations is a height. And what we want to do is we want to find out, you're also given this grid and 2 inputs, right? So the 2 inputs are 2 locations on this grid. So in this case, 3, 1 and 3, 3, which refers to this 4 and this 2 here. So those are 2 villages, and we want to find a location within this grid where we can place a water tank which supplies water to both these villages. And the rule for water supply is that water can only flow from high to low or equal to equal.
Okay. Wow. Cool. Okay. So let me sort of digest this example.
Mm-hmm.
So there's sort of like this mountaintop 7 where it turns out we'll probably want the water tower to go, and this allows water to flow left to 6, right to 4, and down into this valley, but it's kind of lost in the valley because it can't make its way back up.
Yeah.
So it kind of flows down this left branch to 4 and flows down this right branch to 2. Oops, sorry, I didn't do that. And it reaches both of them, and then we win. And if that were not possible, we'd want to find that out too, I think. Is it? Can we assume there always is a successful like point, or is there some inputs? Is it allowed that the input has no valid output?
Yeah, you can have a grid in which you'll not be able to find an answer. So that is totally fine. And if there are multiple answers, you want to return the one with the highest height.
Okay. Great. Okay. So let's see here. So may or may not be an answer. Break ties by value point and okay. Interesting. Um, so I guess conceptually what we have is a grid graph, and I guess it's like a directed graph where a point would have an outgoing edge to each of its 4 neighbors. Actually, wait a second. So how many? One question is, can water flow diagonally or only in the 4 cardinal directions?
Yeah, good question. Only both directions.
Okay, great. Yeah, so a point would have an edge to each one of its 4 neighbors where that neighbor is no taller than the current point. So that's the implicit graph structure in the input map. And then with that, the goal here, I guess, is that we have 2 target destinations, and we want to find a source that has a path to both targets. Um, so, I mean, you could do this by running a traversal starting at every single point, and then if you find one point, like one starting point that reaches both endpoints, then you win. But then you're like doing a linear number of searches. Each one is taking a linear number of times. So you're doing something quadratic in the input size, which is probably less than ideal. So I have a vague sense that maybe you'd want to do the searches in reverse. Like if I take the mirror graph, I forget what the word for this is, but if I take the opposite orientation of every edge, then I want to do like a mountain climbing traversal where I start one traversal from village 1, and I see everywhere village 1 can reach if the definition of outgoing edges is ascending, and then I do the same for village 2, and then I'll have two sets of basically candidates positions for a water tower, and I want to take the intersection of those two sets to get a point, one or more points that are valid candidates for both villages. And that'll give us a linear time algorithm because there's only two villages and each traversal is linear. So I think that's what I want to go with here. There's a lot of details to actually write the code, but I think the concept is pretty clear in my mind.
Yeah, sounds good. And what do you mean by linear here?
Yeah, so linear here is linear in the input size, which is m by n. So O of m by n is what I mean by linear. Thanks for asking.
Got it. Okay, makes sense.
Yeah.
Sounds good. Yeah, you can start coding. Yep.
Great. Sounds good. One question, are m and n both non-zero? Can I assume?
Yeah, you can that they're non-zero.
And the points I'm given as the positions of the villages are both like valid indices. They're in range.
They're in range. Yep.
Great. Okay, cool. So that all sounds good. That, and then, okay. So, wow. Okay. So, maybe I'll have a data type for like the map here, struct map, where the grid is like in this list of are the heights ever negative?
No. Yeah, good question.
Okay, great. So, how do I say this? Water tower location. Choose water tower. And so this will take the graph sort of thing, and then it'll also take 2 points. Oops. Okay. So village 1, say destination 1, point just 2 points, where I'll make that be just like type points equals this for now at least. Looking back at that, and then the goal here is to return a point where I can put the water tower, but if none exists, I'll return none, which is like a nullable returns nullable points. Okay. So the idea here was 2 traversals, 1 from each guest. And then intersection of 2 sets. Okay. So interval ascending self start point maybe reachable soon. So I'll do like a depth first search or something from this function. So how would that look? I would say so let's call it Q equals a new list with starting points in it and see insert start, and then while let equals Q top. Insert her. Oh no, sorry, not scene. Yeah, that's fine. So basically everything that I can reach. When I reach something, I just want to check the neighbors. So like for neighbor in something, come back to this. If not, scene contains neighbor, scene insert neighbor and Q push. So, okay, so we have to figure out a way to generate all ascending neighbors. So, neighbors of points. So we had to function like this, we could then like filter. It's reasonable. I think that's reasonable. Yeah, okay. So this function would be, what would it be? It'd be like, oh yeah, this is old crust. Okay, so like -1, 0, 1, 0, 0, -1, 0, 1 is like the directions. And for each of those, so this is like di, dj, is like rows, columns. Yeah, sure. And then for each of those, like I'm actually gonna make these U size. Because if they're signed, we can not worry about underflow. So anyway, so let I equals, how do I say this? P dot 0 plus di, j equals p dot 1 plus dj, and then like if self dot in range ij, so this should be like a flat map sum ij else none filter map of these guys, and I'll implement in range, which is just the trivial thing. In range self p points cool. And this is literally just like that. Ij equals p 0 less equal I, and I less self grid 0 len, and 0 is 0 less equal j, j less self. So I is rows, j is columns. That. And then I think that's the basic neighbors function. These are like, yeah, return all. So yeah, this returns the 4 neighbors, and then in edge cases like the boundaries of the graph, it returns fewer. So like if I was in the top left corner, this would return only 2 neighbors. So that's good. So the next thing I want to do is be able to filter over which of the neighbors are actually ascending. So I'll implement a function get self point. I'll just have this always get a value. So like self range p sort of as a comment, and then I wanted to say self grid a equals p self grid I j is all that is. Yeah, cool. Okay, so then I just kind of want like self neighbors of p, but then like filter on p2 should have self.get of p1, it's like either greater or less than, figure that out, of self.get of p2. So let's see. So I want to climb mountains. I want to find things that are taller than me, so I can do this. I think that's what I want there. So find me all neighbors of p, which are points p2, such that p2 is at least as large. And so I'm mountain climbing, and and that should be what I want. And then I just need to call this function twice and take 2 intersections, and then return, I think. So that means one is, hashtag new self reachable ascending of one by reference. Two, and I intersect these 2 guys. So like one, I think literally intersection between 2 is an iterator, and I want the max. So max by key p self.get p. So and not unwrapped because yeah, so this should correctly be empty if it's empty and well, max, yeah. I think this is actually just what I want. So, I mean, that might be it. Modulus and compiler errors. So, yeah, why don't we just sort of compile and see if this works? And obviously it doesn't. So let's see here. All the way to the top. So hash set is imported like this. Hash set. We need a main function. Do nothing for now. Hash set. Can I find a value p? I call it something else. I call it cur. Let's call it p for point. It's fine. Main function, yeah. In range takes. Sure. Where am I doing that? It's in this. That's fine. I could say. Okay. Okay. And what else? Mismatch types. So on line 23, 27 now it says. Oh yeah, it says just need to borrow that and pointer copy. Okay. That cannot be indexed by I size. That's true. So these we need to cast such, and the comparisons here will actually be the same. Where it's like this size. Okay, I think that's it. Let's try that. Okay, a semicolon somewhere and anonymous lifetime. Oh yeah, that's true. This is a neighbors. This is true. Okay, think about this. So technically, I mean that's fine. Well, simplest way is just to do this, but that should work. Else, okay, we'll need to take ownership of some things. Just move the point, and then that should work. Okay, we're very close. So no method named intersection. There's a method with a similar name. Did I just misspell it? Inster. Okay, yeah. Intersection. Let's try that. Types. Max by key. I just need to get that twice. Is it really twice? Okay. Okay. Lastly, I get a point. I wanted a. I'm getting a no. I see. Copied here and pick one of these up. Okay. Cool. So the code compiles to start. I'll comment out the other stuff since it's unused. Or maybe I'll just say it's really public. Does that sound? Yeah. Okay. Great. So let's try to run this code. One sec. So the input is it's a list of lists. Okay, let's try this. Okay, that's a grid. These are points. Okay, so we want to say like a map grid, and then map choose water. And then just sort of like I guess put them both debug. So search equals Yeah, let's try running this. So we got 1, 2, which I guess was what we wanted. Cool. Okay. So yeah, I mean, it seems to just work.
Awesome. So yeah, so once you're done with this, can you explain what are the additional test cases you'll test this with, and then we can move on to one more problem. Yeah.
Sorry. So you said runtime?
Not the runtime, but just like what additional test cases will you test this with?
Oh yeah, tests. Great idea. So the smallest edge case is like one single point. I guess I didn't clarify this in the question, but I'm assuming I'm allowed to place a water tower in a village. Um, and if that's the case,
Yeah,
okay, cool.
that's a good question. Yeah, let's say like we want to find a water tower which is outside those two villages.
Interesting. So then that's we can do that too. So we just have to make sure to kind of
Mhm.
filter the list here. So
Yeah, don't worry about changing anything. Yeah, that's just this is just a discussion.
sure.
You don't have to change
Yeah,
anything.
yeah. So what we'd want to do is just make sure that we are never returning either village themselves. So we would do the same
Mhm.
calculation of things we can reach, but then from the intersection we exclude both P1 and P2, or dest1 and dest2. Um,
Mhm.
so we just filter by not equals 0.1, not equals 0.2, and then that would make sure we never choose those 2 points, and we choose anything but it, and potentially this makes an empty iterator, which we'd then return nothing, and otherwise we'll still return the right thing, breaking ties with max.
Um,
Does that make sense?
yeah. Mhm.
Filter not equal to P1, or P2. Yeah, so that would be that. And then yeah, test cases, I guess like I was saying, like a grid of size 1. With this interpretation, there's no solution, so that's one test case. A grid of size like 4 would be maybe the smallest where there is a solution. So you could test a couple of grids of size 4. Maybe test like a column grid where there's like a one-dimensional, input, and where both the case where there is a solution and where there isn't, and then similar for a single row input. And then so those are all the kind of smallest edge cases. And then other than that, just test some medium-sized inputs, test some graphs that are like, kind of maze-like, like not super trivial to traverse, and then test like one big input for performance, something like that.
Okay. Sounds good. So for the last question, for this one, we may not have enough time to write code, but we can just discuss. So on line number 1,
Mm-hmm.
let's say you give an array and a window size, right? So you have an array 1, 2, 3, 4, 5, 6, 7, and you have a window size, let's say 3, right? And then we want an output which is going to be the max of each window from left to right. So the first window is 1, 2, 3, max of that is 3. Second window is 2, 3, 4, max of that is 4, and then so on.
Okay.
Yeah. So this is the question.
Great, that sounds good. So is the window size a parameter, or is it always 3?
Yeah, it's an input, right? So it's
Okay.
dynamic.
Great. Yeah, so if that becomes something like n over 2, then it starts to matter what data structure that we maintain the window in. So naively, we could do this with, how do I say, just doing a linear scan through the window to find the max, but that'll take us n squared time, the naive thing. So let's see. So instead of doing that, I'm guessing we want to do something sort of online, sort of sliding windowy from left to right, where we maintain a data structure, like probably a priority queue, which we insert, well, maybe not a priority queue. Let me think about that actually. Maybe an ordered map, like a binary search tree or a B tree. So we want a collection of the numbers we've seen so far, and we want to be able to insert one number when like we kind of update the window to extend it by one, and also remove one number when we're shrinking it by one, like so that we're sliding it over by one and keeping the size the same. So obviously a data structure that allows an insertion and a deletion by the key, which is the number. But then beyond that, we also want to know the maximum efficiently. So a heap's actually not a good choice for this because I think insertions and deletions aren't trivial. I mean, it's possible actually, but most heaps you can't delete from the middle of the heap. They only access to the top. But that's an implementation choice. But so let's say not a heap, but instead like an ordered map, which in Rust is like a B tree map or a B tree set, let's say. So this is like a half set. It's maintaining, well, let's see, I guess not a set. Maybe it'd be a map from like value to like the frequency of that value or something, or like if these are, I don't know if this is signed or not. But so this is like the frequencies of the sliding window. This frequencies just like this, and then so that way I can maintain the sort of state of the window, and I can update it in log time, each iteration of the loop to compute each output, and so log w updates. W update, and the computation of the maximum is also log w max. So then I'd get an algorithm that's like n, n minus w iterations, but like say something like n in the worst case, and then, well, see, n minus w. I mean, I guess I'll write it like this. I'm not sure if this is overcomplicated, but n minus w and then a log w. This is like what you would end up with this approach. Is the approach pretty clear how that would work?
Somewhat. Yeah. So I have a few questions. So this frequency map, can you talk more about it? Like, is it maintaining the counts of each values, or?
Yeah, exactly. So if we had like 1, 2, 2, 3, 1, 4, and the window size was like 4, then the first window is 1 has 2 copies and 3 has 1 copy. And then as we update the window, this will go to, let's see, we'll get another copy of 1, so this becomes 2. And we lose a copy of 1, so it stays the same. But then the final window would look like we would lose a copy of 2 and we'd get a copy of 4 in the last window, like this. Does that make sense?
So you shift the window and then you update the frequency. And then based on that, you also reduce or increase the frequency, right? So, yeah. And then you find the max, because it's a binary tree, you'll be able to find the max. How do you find the max? Like, do you look at the right node, or is it like a binary search?
Yeah, it's a lot like a binary search tree. Like the B tree idea is just sort of an optimization of the concept of a binary search tree. The main idea is the same. So essentially, yeah, you just call the helper function that does it. It's because it's in the standard library. But what that would be doing is it would be traversing like the right spine of the tree, and then basically, yeah, you go to the right until you can't anymore, and then you stop there. And it doesn't have to be a leaf, but it will be the largest key in the tree. Does that make sense?
So, yeah, and that would be what would be the maximum depth? So if you want to find the rightmost node, what would be that?
Yeah. So since this is a self-balancing tree, it's probably like a red-black tree or ABL tree. The maximum depth is logarithmic in the size of the tree, which is W, so log W.
Got it. Okay, so just let me make sure. Yeah, I've never seen anybody give me this solution, so I'm just thinking about it. Is it? Yeah.
Okay.
So yeah, the frequencies, and then okay, and then you want to find the one with the highest value. So are these So are these indexed by like the value or indexed by the frequency?
Yeah. So keys are values. Values are frequencies.
Mm-hmm. So
Yeah.
when you try to find the max, right? So will they be searching for the maximum? I'm assuming like the maximum key and like the highest key, right?
Yeah, exactly. The max key, but I guess it's important to mention that deletions from the tree, you have to check, like after decrementing, you have to say, is it now 0? And if so, remove the key. Because you would not want something like this, because that would mess up the algorithm. So just make sure that all the values,
But
freaks are non-zero.
makes sense. Yeah. So this sounds good. But sometimes like some interviewers can ask you to use like a data structure which you can write from scratch, right? So
Okay.
this one you're sort of relying on a library. So
Yes.
it would be good to think about can you use something else
Mhm.
to write the code for this, right? So that yeah, you can think about it later, or you can look at the solution online. And there are like two approaches. One of them is linear time, and one of them is nlogw.
Okay. Interesting. Yeah, I'll have to think about that. Huh.
Yeah. Um, yeah. If you want, you can think about it. You have like 2 minutes, and then we'll jump into feedback. Yeah.
Sure. That sounds good. Linear time is interesting. It's kind of surprising almost because oh, maybe if you had linear extra space, you could do something clever where or you like keep a stack or something. I don't know. Like
Mm-hmm.
I'm not entirely sure, but there's probably something quite clever. um,
Mm-hmm. I can give you one hint, which is like you want to maintain a data structure which stores all your max candidates at
mhm.
that point. So when you iterate over these numbers, wherever your I is, so let's say on line 1, if you ingest 1, then you update your max candidates to 1. If you look at, and then you look at 2, and
Mhm.
then you see whether you need to do something with this max candidates, right? Like, do you need to update the list, or do you need to keep adding to it? Yeah.
Right. Okay. Let me think about that. So the thing that seems a little tricky is like if you had like 3, 2, 1, and then I don't know
Mm-hmm.
what it is, like 2, 2, 2. But the initial window it has 3 things in it, but you'll have to somehow know to reduce the max once you shift the window to the second iteration. So that's
Mm-hmm.
kind of tricky. Hmm.
Yeah, like one insight here is, so let's say like if you have an input like
Mhm.
3, 2, 1, and then if you have 3, 2, 1, so let's say like you look at 3, right? So 3 goes into your max candidate
Okay.
data structure, right? So 3 is there, and then you look at 2. So you decide whether you want to keep 2 or whether you don't really need to keep 2, right? So because
Mhm.
2 is smaller than 3, so do you think you'll need to preserve 2 in this max candidates list, or you think it
Well,
doesn't matter if you? Mhm.
I think I might because like if these are all ones, the 2 is
Mhm.
relevant during this window. Like this should
Mhm.
output 2.
Exactly. Yeah,
So
because
yeah.
yeah, because two can be a max in the future, right? Once 3 slides out, 2 can be a max in the future. But let's say like this number was now 9, right? So
Mhm.
now you have ingested 2 and you're looking at 9, and so far your max candidates has 3 and 2. So 9 is coming in. What do you think about 9? What do you need to do?
Well, I guess 9 is like better in every dimension because it's both bigger and it's farther along in the list. So I'll have access to it for like longer time. So I
Exactly.
clear the whole list. So are these
Yeah.
elements of the list like tagged with their index? So like 3, 0, 2, 1, and then when I see 9, and I know that it's bigger, sort of like a 9 is what 9, excuse me, 9, 2, and then so I'll compare until I find, but then interesting. So I'm clearing the stack, and then if I find things, I see. So okay, I think I have a general idea of it. Like, and then later you'll clear the stack in this case, and later when you see like 1, 3, you know that 1 doesn't dominate 9, so you won't clear 9 from the stack, but you will push 1 to the stack, I think.
Yeah, because 1 can be a max in the future, right? Like because 1 comes after 9.
Yeah, exactly. Is this actually more like a queue instead of a stack? Because you're kind of popping from the left as well when you're like invalidating like
Mm-hmm.
the time that the thing has left to live. So yeah, I'm guessing it's like a queue, like a circular buffer thing, and you're like both. It sounds kind of tricky, hard to write the code maybe, but you're popping from the left when things expire, and then also you're clearing the queue when you find something that kind of strictly dominates the contents of the queue, or like you're clearing as much of it as you need to, and then I guess
Yeah.
something like that. Yeah. Wow.
So yeah.
Sounds
So
pretty
let's
hard.
talk.
Mm-hmm.
Yeah, let's talk here, and definitely look into like mono queue and mono stack pattern.
Okay.
Right.
Cool.
So
I'll take a look at that.
this kind of like semantics of like adding things to the queue, clearing them, and then your max is always going to be available. Max or min is always going to be available on your left or the right.
Okay.
Yeah, so that pattern is mono queue and mono stack. Um,
Neat.
okay, so I think like today, like overall, like it was great. You asked a lot of good questions. You wrote really great, really nice code, really nice function names, modular code. I think it was similar to last time, except that maybe like the debugging was faster this time, right? Yeah, just be whenever you're going to like actual interviews, just be aware of like what Rust version you'll be running and like try to code accordingly,
Right.
so that you don't have to on debugging. And then you talked about time and space, so that is good on your own. And one minor feedback would be, yeah, just like whenever you're done coding, try to talk about like walk through, take an example, do a walkthrough with it, and then talk about additional test cases. Right?
Okay.
Yeah, that'll be just the being proactive after you write the code.
Yeah. Great.
I think, yeah, that is it from my side. Like you solved all the questions, good intuition on all of them. Yeah,
Yeah. Yeah. Awesome. Thanks. Thanks so much for the practice. This was super helpful.
awesome. So yeah, have a good day and all the best.
You too. Bye.